Good evening, everyone. I'm Cai Songlu, the architect of Alibaba Cloud Database. My colleagues has done the introduction to Alibaba Cloud and Cloud Database. Now I'm honored to have such opportunity to share our works on cloud native database, as we call Impala DB. At first, you may ask, what's the exact meaning of cloud native database? What's the standard of a cloud native database? How we define it? And why we define it in such a way? Okay, now let's put these questions behind us. We will answer it later. Now let's take a look at what a cloud native database looks like. I call it the threshold of a cloud native database, or the basic properties of a cloud native database. First, it must be with outstanding performance. It can serve a million requests per second. Second, it must be with large-scale storage. The storage can be up to 100 terabytes. And third, it's very important that we have the zero downtime capability in the cloud. Last but the most important one, the cloud is an ecosystem. You must be compatible with the open source solutions. The cloud native database is like a sports car. A sports car also has some properties like the outlook, the speed. But a car with such outlook and speed may not be a sports car. So back to our questions. What's the standard of a cloud native database? Before answering it, let's take a look at the evolution of the database. I conclude from 4 dimensions to show the evolution. First, the data scale. Now we are in a data explosion age, and some series also changed or evolved, especially the CP/CRM. We also have some breakthrough in algorithms, for example, the Pegasus or Raft. The users and the scenario also change. The infrastructure moves from the IDC to the cloud. And now everything is online. So how and why of data explosion? The data sheet is cited from the Internet Queen Makers report. As you see, we can divide the Internet history into 3 stages. The first stage, we call it the PC Internet. Nearly all the data is generated by personal computers. The second stage, we call it the mobile Internet. And nearly all the data is generated by the smartphones. Yes, now I think we are in the mobile Internet age. And the third stage, we call it the IoT stage. I think maybe all the data is generated by sensors, by your watches, by your cars, by your refrigerators, by your home lights, by everything. With the data explosion, there are coming challenges. Data in large scale means that the increased expense on storing and analyzing data. It's also hard to transfer and analyze such big data. In a word, it's hard to utilize. In recent years, some basic series of a distributed system also changed a lot. CP is one of them. The CP/CRM is introduced in 2000. In this CRM, C is consistency, and A is availability, P is partition tolerance. The point of this CRM is that C and A can't be both promised at the same time with P presence. CP is a great CRM, but there are lots of misunderstandings of this CRM. One of the misunderstandings is that C and A is mutually exclusive with each other. So some systems choose one of them in order to achieve the other one. like some NoSQL products. But in fact, the relation of C and A is not 0 to 1. I think it is 100% to 99%. More precisely, C and A can't be perfectly promised at the same time. Now, we can also model the P problem as an A problem. P is mainly caused by netlink hardware failures, the switch failures, or maybe the bad root configuration. Let's take a look at such case. One node is partitioned due to the network hard failure. All the requests to this node will fail. But if we can remove this node automatically, then the requests will retry and forward to the healthy node. In fact, when a node crashes down, our system will process it in the same way. So basically, P and A is the same in some cases. So how can we remove the failed node automatically and promise the consistency at the same time? We can use the Paxos algorithm to meet the needs. Paxos can guarantee the consistency, and Paxos only requires that more than half operations are successful. For the crash, partitioned or slow nodes, we can tolerate it and remove the failed node automatically. If more than half nodes are partitioned in several partitions, we choose consistency and give up the availability. But in the real world, it is very, very rare. So in most cases, we can model the P problem as an A problem and promise nearly complete C and A at the same time. "20 years ago, only the giants like the government, the big company, could use a database. Now all the business from the giants to the tiny ones runs on database. And the requirements for database change a lot. First, the database should be more flexible. Sometimes we need to do a market activity, like the Black Friday. We don't know the real traffic on that day, and sometimes hotspot scenes come in sudden, like the 9/11. The traffic is a burst and unpredictable. We want the database to be flexible and easy to scale, and the business is transparent due to the globalization. There are many users making small business. They want a more economical solution. And the customers are demanding and sensitive to the RT latency. The faster the database is, the less of the customer loss. And last, the database should be more agile to every potential problem. When failure comes up, the database should react rapidly and recover as soon as possible. In a word, the underlying requirements for the database are elastic, low cost, outstanding performance, and a continuous solution. Now everything is online. Before the cloud age, the data is in IDC and scattered everywhere. Now the data is in the data lake. It is generated and then applied to the training model at the same time. So it's online generated, analyzed, and applied. Our life is also online, like eating, clothing, transportation, working, social activities, and entertainment. You can live in-house for a year just with a smartphone. Your customers are always online. They are all over the world, never log out day and night. Now in China, 70% of uprising enterprises are hampered by such data challenges. High cost, they can't afford expensive license, and lack of professional engineers. They are with strong will but weak ability. It is hard for them to deal with data backup, the data mining, the troubleshooting, and such things. Their data is islanded, scattered, separated everywhere. The data is sleeping, offline and wasted. But it still continues to explode. It is hard to store, move, and analyze. So with the evolutions mentioned above and the coming up data challenges, we think that a cloud-native database should be with such standards. First, a cloud-native database is not only a TP database, it is also an AP database with TP and AP together. We call it the HTAP. We benefit a lot from the HTAP architecture. Second, a cloud-native database must be serverless. With serverless, we can largely cut the cost, and it must be smart and intelligent. Like an advisor, can do diagnosing and management jobs. Through this, we can improve the experience and keep users from the boring and tough things. Okay, let's talk about them in details. In HTTP, TP and AP share one storage. So there's no lag for analytics because there's no need for syncing data. You don't have to sync data from the master to a read-only slaves. And it's real time. It is good for time-critical business. Now TP and AP share one storage. It is saved at least one data copy. For the computing layer, AP is separated with the TP by containers, so AP do no interference to TP. With such separation, TP and AP computing nodes can be scaled up, down, in, and out easily. For serverless, it is zero cost for product upgrade. The computing node is containerized in lightweight container. The life cycle of a session is short. So when we do roll up upgrade, the clients feel nothing about it. Now you can pay for use and just pay for storage. The computing cost is low. You can also set different storage strategies for the computing and the storage layer. For the busy business, you can use more memory or SSD for storing. For the idle business, you can store the data in HDD disk. It can save you cost dramatically. For intelligence, the advisor will analyze the data generated by the instance. For example, the CPU, memory, storage usage, and the watermark, and give you SQL and index optimization advices. It behaves like a professional DBA and enforces the user of the professional DBA. When some faults happen in the data path, the data path is so long and so deep that we don't know where exactly the fault happened. We got a monitoring and a diagnosis system. With this system, you can easily diagnose the whole path and get the root cause immediately. It can also do some management works like the cost control, safety, and audit. With the guidance of such standards and the thresholds mentioned above, we forge a cloud-native database, Impala DB. I will share the architecture, products design, and the future works of Impala DB. This is an overview of Impala DB architecture. The upper layer is a computing layer. The lower layer is a storage layer. The computing layer is separated with the storage layer. They are connected by the RDMA network. All of the logics run in the user space and bypass the Linux kernel. In the data path, we implement zero copy. We also implement a Raft variant, parallel Raft. We call it a P-Raft. It supports out-of-order commit, so it is much faster than Raft. In Impala DB, we apply new hardware to improve the performance and cut the cost. It is designed for next-generation hardware. For the computing nodes, there's only one write entry. The read-write node has the read and write requests. Other nodes are read-only. They can only handle the read requests. For the storage nodes, we use P-Raft to write 3 copies of data. Why do we separate the computing with the storage? First, we can apply different hardwares for computing and storage nodes. For computing, we focus on better CPU and large memory. For storage, we focus on fast and low-cost disk, so they can be separately customized and optimized. It is easy for the computing nodes to do failover and migration because the computing nodes is stateless and has no data. For storage, we also improve the replication and HA performance. And now the storage, like a pool, is managed in chunks. So there's no fragmentation, no imbalance among nodes, and it's easy to scale out. With such architecture, it is easy to implement the serverless. So you can have no computing nodes when your application is idle. In Impala DB, everything is in user space. A request is issued by the database agent. The libpfs will map it into I/O requests. The port switch forwards the I/O requests to the storage nodes. The network is RDMA, and the data is written into the remote buffer. They handled by P-Raft leader. Durable to disk by SBTK, then synced to other 2 followers through RDMA. In the whole path, there's no syscall, and so there's no context switch. No context switch and zero copy makes Impala DB a crazy fast database. Okay, this is an illustration of Impala DB file system PFS. It is with POSIX API with low invasion to database agent. PFS is a library and statically linked into the DB server. PFS is a distributed file system. The metadata is synced among nodes with the Paxos algorithm. So it permits concurrent operations. There's also the metadata cache in each node. For acceleration, the cache is invalidated by the version control. For understanding PFS, we'll give the analogy of a PFS and the file system terms. Volume is like the mountain port, and metadata is like the superblock, etc. We use the P-Raft to sync 3 copies of data. P-Raft is a variant of the Raft. Raft doesn't permit out of order commit and holds. The restrictions make Raft slow and with low throughput. In Raft, we allow out of order commit, acknowledgement, and apply. The transaction semantics and the serializability is promised by the database engine. For holds, we have catch-up mechanism. It is a complex process. We give the detailed illustration in VLDB paper. It is just yet accepted. Okay, in Impala DB, we explore the new hardwares and maximize the capability of the hardwares. Besides the RDMA, we are also working on open channel SSD to maximize the value of SSD. And we are working with the Intel Opton team to boost the storage layer. And at the end of my speech, we will invite the manager of the Intel Opton team to do the introduction. This is the benchmark results of Impala DB and the RDS format SQL. We use Sysbench to do the stress test. The purple one is Impala DB, and the pink one is RDS. From the numbers, you can see that with similar resource for read, averagely, the performance of Impala DB is 6 times of RDS. For write, it is 3 times. So it is a great improvement. Now let's take a look at the product features of Impala DB. For performance, it is easy to scale up to 1 million QPS, and the response time less than 2 milliseconds. The capacity is easy to scale up to 100 terabytes. For elasticity, it is easy to scale up and scale out, and zero downtime for upgrade. For compatibility, it is 100% compatible with MySQL. For availability, when force happen, we prefer consistency to availability. So now we promise 3 nines availability, and for data reliability, we promise 5 nines. In Impala DB, the read and write is split into different nodes. There's only one writable node. It can handle all kinds of requests, a read request and a write request. There can be many read-only nodes. The write QPS can be scaled to 130,000. The read QPS can easily scale out to several million. For scalability, it is easy to scale up down for all nodes, scale in and scale out for read-only nodes, scale up, scale down for storage, scale in and scale out for storage cluster, and zero downtime for failover among the read-write nodes and the read-only nodes. For data migration, you can boot your Impala DB instance with a backup from the OSS. OSS is like the AWS S3. You can replicate the data from the RDS instance, make Impala DB as a slave. You can also use the DTS to transfer data from RDS or other database to Impala DB. DTS is short for Data Transfer Service in Cloud. For data reliability, we can fail over in several zones in one region. You can start a standby instance in another zone and replicate the data with redo log. For failover in regions, we always use a bin log replication. For backup, you can make a snapshot in seconds. and transfer the snapshot to OSS. Okay. These are our future works of PoloDB. Now PoloDB is just a baby. We still have lots of works to do. In the DB engine layer, we will support multi-write. Right now, PoloDB is a shared disk architecture. We are heading for the share everything architecture. For example, in the computing layer, there will be a central cache fusion to boost the query performance. We are porting more databases to PoloDB, like more MySQL editions, PostgreSQL, and our document DB. For the storage layer, we are working with the Intel Optane team to boost the I/O performance, and we will improve the performance of SSD with open channel, and we will put more InnoDB logics to the storage layer. We call it the Smart Scan. It will save much I/O and make the computer layer much easier. Alibaba's basic idea is that Scholar for engineering and engineering with Scholar. There's no pure Scholar, and there's no pure engineering. Our team has submitted several papers to Sigmod and VLDB. Recently, they will be published. I think you will see more detailed information about PoloDB and the storage. We are also recruiting at Europe. We have office in Paris and Germany. You can scan the barcode and see more detailed information. You can contact with us if you are interested. Thank you.